So this presentation is part of a series of elimination reaction presentations. So we are still in the reaction types, which is substitution and elimination. So we're focusing on elimination reactions. But before we start that, we need to understand the nomenclature for alkenes, okay, and its properties. So that's what we're doing now. So first of all, alkenes are hydrocarbons with a double bond. So they have at least one double bond in there. The formula is supposed to be CnH2n, as you remember what we did from functional groups. And the carbon that has the double bond is sp2 hybridized, which is a 120-degree bond, and it's trigonal planar. Now, when you draw it out on 2D, like on a paper, it's going to look like it's an sp3 carbon with the similar kind of bond angles like here, but it really is different. Okay, and again, making a model set really helps to see how it looks in 3D. So then, me and I classify, alkenes as being terminal or internal also, because it helps us to understand reactions and how to synthesize some of these double bonds. So it's much better we talk about this right now. So there's a terminal double bond, and an internal double bond would be somewhere within the chain, inside. Terminal would be usually at the end, okay? And it's not like a organic classification. This is just my thing. I keep saying it, so I just want to clarify that. And then finally, you can also find double bonds in cyclic compounds. Cyclic means like, cyclopropane, cyclobutane, but then with a double bond in it. Those kind of double bonds will always be internal, right? Because they are inside a ring. So let's look at the nomenclature first, okay, to get started. And the smallest alkene possible, as you know, is a 2-carbon, okay, because a 1-carbon alkene will not be possible. There'll not be enough bonds for it. So the first alkene is ethene. There are, I think, no general names to talk about here, okay? So we'll just keep focusing on the IUPAC nomenclature, which is the standardized nomenclature. So ethene and then propene, okay? And then once you get to butene, which is, 4 carbons, now you have to talk about where the double bond is, okay? And so here the double bond is terminal, here it is internal, which means that these two are constitutional isomers, okay? Because they're not the same compounds, they are alkenes, but they are not the same compound, okay? So constitutional isomers. So now you have to indicate where the double bond is. So now you have to give the locant, okay, for the double bond. So in the case of the terminal bond, this is going to be but-1-ene. 1-butene, 1-butene, that's the old name. If you want to use it, you can. For me, you can. Sometimes I do it too. But really, this is the new nomenclature. And it is really very simple. And it is also very, it's more functional than the old one. That's why they went to the new one, because now you have the locant just before the functional group. Okay. And so if you have 3 or 4 functional groups, then it is just easier to go ahead and put the locant just before the functional group itself. So it's a lot more helpful. So I will encourage you to use this, okay? But know that this also it's fine if you're not thinking about this, it's okay. All right. So then this one here is going to be but-2-ene. So 2 meaning 1, 2, 3, 4, right? So 2-ene over here. Now, once you start getting longer chains, okay, and the double bond is not, in butene, it's kind of symmetrical, right? In the first one, of course, there is, so starting from the end over here, and here, whether you start from left side, it's 2, if you right side, it's still 2, okay? So, but when you start getting longer chains, okay, then you have to remember that the double bond should get the lower number, and also that you should include the double bond in your numbering, okay? So the lower number should be at the double bond, and then, it should be included in the long chain, all right? Don't start from here. You'll understand what I'm trying to say, okay? So this one is pent-2-ene and not pent-3-ene or anything, okay? So now for the substituents, and in the case of alkenes, And as we get to learn more functional groups, you will see that, functional groups get a little bit more priority. And so here also alkenes get more priority than substituents, which means that you have to start numbering from the double bond and not from where the branching is. Okay, you should still try to get the branching a lower number if possible, but really the priority is for the double bond. Okay, and so here the methyl group is on the second carbon, and then the double bond is on carbon number 1. Okay, don't give it number 2. Okay, don't give this carbon or the alkene a location of 2. It's not 2. Okay, because the double bond is between 2 carbons. Okay, so always give the lower number, the alkene. All right, so here it is your name, so 2-methyl-hex-1-ene or 2-methyl-1-hexene. Okay, both are okay for me. As I said, I would encourage you to get used to just this one. I gave the old one just in case you see it somewhere and you wonder what that is. Okay, so these are just examples of how you would number and name alkenes. So again, the red ones are the ones that are wrong. Okay, the blue ones are the correct ones. And again, in all of them, you will see that you have to start numbering from the alkene, okay, or whatever is closest to the alkene. So in this case, the alkene is an internal alkene, so you number closer to the alkene. Here, the alkene here is going to be the terminal alkene. All right, so even though the ethyl group, it might seem, oh my god, but this is the long chain, that's not the long chain. Okay, so this becomes the ethyl group, it becomes a substituent. So just watch out for that. Okay, a little bit. Always have alkene as your lowest numbers. Okay, and there, start the numbering from there. In case of cyclic compounds now, for cyclic, a simple like the cyclohexene would just be cyclohexene. You don't have to indicate where the double bond is because it could be anywhere and that's fine. Okay, but as soon as you have, a substituent in there, then you have to make sure you name the substituent also. Again, if you just have the one substituent, no numbering is required because the substituent could be here or here. Especially if it is on the double bond. Okay, if it is not on the double bond, then you need numbering. Okay, if it is on the double bond, then you don't need to give the location. But then here you can see that the methyl group has shifted. Now it's not on the double bond. So now you have to give the location of it. So where do you start the numbering from? Okay, so I've given you two numberings over here. And in the first case, the blue case, which is the correct one as usual, you have to include the double bond in your numbering. Okay, so 1, 2, 3. So 3-methyl cyclohexene. Now it doesn't say 1-hexene. Okay, that's because the number 1 is the double bond. So you don't have to give the location for the double bond. All right, so you don't need that location for double bond. Now the red one you can see here, and you're probably thinking, well, I would have done this because it gives lower numbers to the alkene as well as the methyl group, but that's not the rule. The rule is to include the double bond when you are counting. Okay, so the blue one is the correct numbering here. So again, not again, this one is a little bit different. So here, you number, in a ring, it's a little bit challenging because sometimes your view may be a little bit warped, you may not be seeing things. So always number. Okay, it's always better to go ahead and number one way and then number another way to see if you're getting lower numbers, okay, in there. So if you see this one that I've numbered for you, the blue one has the lower numbers, okay, and the red one has the higher numbers. So always go with something that has lower numbers. And again, whenever you are in doubt, okay, write it out or draw it out and then see what it looks like, okay, before you make your final decision. Now let's look at something that is characteristic of a double bond, which is cis and trans. So you might recall the cis and trans we encountered before was in cyclic compounds, and that was because you can't rotate ring structures, and so wherever the hydrogens were, they were stuck there, right? So if you had, them at the same place, on the same side, then that was cis, and if the hydrogens were on the opposite side, they were trans. It's the same here for double bonds, because double bonds also cannot be rotated. You can rotate a single bond, an sp3, but sp2 you cannot rotate, because if you try to, you'll break the double bond. Again, you can use models to help you out, okay, if you want to. Anyhow, so there is cis and trans in alkenes as well. These are called geometric isomers, just like they were called in cyclic compounds as well. Okay, so again, cis is when the two hydrogens are on the same side, and trans is when they're on the opposite sides. Okay, so let me show you what they look like. So here is an alkene with the two hydrogens on opposite side, that's trans, and then if they're on the same side, then this is what it looks like, it's cis. So I've just rotated the whole molecule just so you can see they're on the same side. I mean, this also shows it. But this was drawn as a zigzag, right? So like that. So here is the line structure for the trans, and then here is the line structure for the cis, okay? The line structure for the trans, you can see, is just like a line structure for an alkane, right? Zigzag, zigzag, kind of you keep going on. But the line structure for the cis is a little bit different, okay? And this makes a huge difference as far as the 3D structure of the molecule is concerned. So not only for organic chemistry, as in like how the reactions will take place, but also in our body, how these cis and trans molecules will react and behave is very different. Okay, and we eat alkenes all the time. Okay, one of the biggest alkenes that we eat are going to be the fatty acids. Okay, and the fatty acids have double bonds in them. And so how are those double bonds? Are they trans, or are they cis? And which one is good for you? And if you go grocery shopping, then you will see that a lot of products will say zero trans fats, so it means the trans ones are probably bad for you. But why are they bad for you? We will talk about that at some point, I think maybe towards the end of the presentation. But anyhow, okay, so it's a huge difference in a 3D shape of a molecule. All right, so this one is trans, this one is cis, and this is for butene. All right, because this is just a 4-carbon structure. So we did butene before. I didn't bring the cis and trans up, but now we're talking about it. Now, how to write this? The best thing to do is to write trans in brackets, okay, dash, and then butene, all right, and cis then is written as a bracket as well. You can write this as an italics, but it's kind of hard to do that when you're handwriting anything. So the best thing to do is just use brackets, okay, over here. Now, one thing I want to mention about the terminal double bonds, when you have terminal double bonds, then you don't have cis or trans, okay? Because what do? This is cis or this is trans, what is this? So you don't really have a cis and trans or a geometric isomer if you have a terminal double bond, okay? Now you can see why I like doing terminal and internal, because internal double bonds have different properties than terminals do, okay? So anyhow, that's your basic nomenclature. Let's move on. Now let's look at compounds that don't have the hydrogens, okay, in there. So if you have two hydrogens on the same side, it's cis, and then opposite it's trans. But what if you don't have hydrogens? So in these compounds that I've given you here, it's the same groups, but look at the way they are attached, okay? It's all different. So here there is no hydrogen, but you have two methyl groups, but the methyl groups cannot be trans or cis. I mean, you can call them that, but they really are not, okay? Nomenclature wise, they're not, okay? So in order for us to name these kind of compounds where they have a particular relationship, and the reason they have that relationship, remember, is because their location drives the 3D structure. Okay, what that means is in order for you to get the Cl on the same side as bromine, like here, or bromine as the same side as Cl, you would have to break this bond. You'd have to break the bromine bond, you'd have to break the methyl bond, and then interchange these atoms or groups in order to get the bromine and Cl on the same side. So when you're breaking something, it's completely different. So, it matters a lot. And so how do you name these compounds which don't have hydrogen? So again, Kahn and Gold pre-log to the rescue. And now we use E and Z system for this. Remember, we used R and S for absolute configuration in stereochemistry. So now we use E and Z for double bonds, okay? The good thing is, of course, that you don't have to learn any new priorities. It's all the same thing, okay? The rules are the same, except that you just have to figure out some things. And so that assignment, how you do it is by taking the double bond and by slicing it in half. So here you kind of, slice it in the middle like this, and then you look again atom by atom by atom. Okay, so you look at the atom on one side, atom on the other side, and assign priority according to the atomic number, higher, lower, same thing for the other side. Okay, and so if you have the groups on the same side, that's then it's going to be Z. Okay, and then if it's on the opposite side, then it's going to be E. Okay, and these are the I think they're German words, okay, for on the same side and on the opposite sides. So again, you have to divide the double bond into two, and then assign the priority according to atomic number, and then see if one is lower or higher. Now remember, assigning the priorities is the same as before. Okay, nothing has changed, which means you go atom by atom and according to atomic number. All right, so here is your guideline for E and Z nomenclature. So here now, if we take butene again and decide to do the E and Z nomenclature instead of cis and trans, then what you would do is slice it in the middle, and then carbon and hydrogen, right? So carbon on one side, hydrogen on one side, carbon is larger, and on the other side, same thing, carbon and hydrogen, carbon is larger. So same groups, not same groups, larger atomic groups or heavier groups are on one side, on the same side. I guess I should be a little bit more drunk on that, but anyhow, so that's going to be then Z here, and then here it's going to be E, because now the bigger atoms are on the opposite sides. Okay, and again, I'm saying atoms and groups and I'm interchanging that, I realize, but in this case you can easily say groups, okay, because it's just hydrogen atoms. When you have larger groups, like ethyl, methyl, and then you're comparing it to T-butyl, then those, I mean, you can use groups also, but you have to go atom by atom first. Okay. All right, and then here is another example of what the nomenclature would look like for, or assignment would look like for this. I don't think I've given the name. I do have given the name here. So anyhow, so here is another structure. So you slice the double bond into two. On one side the carbon is the heavier, on the other side the Cl is the heavier. So this is going to be an E configuration, and now you can name it also. Okay, so 1, 2, 3, 4, so 2 chloro, 2 butene. Okay, that's the name for this compound. Here are your rules again for priorities. So this one you've seen before when we did stereochemistry, so I'm not going to go over it because you know how to assign priorities. In this case, it's just looking at the atom. Here, if you had, the first atom is the same, and then you're looking at the second atom in order to assign priorities. Remember always to go atom by atom by atom. Don't go by group. Sometimes you can take shortcuts, and like I've said, double bonds weigh more than single bonds, triple bonds are more than double bonds. That's fine, that's okay, but sometimes it doesn't work, all right, because you have to look at the other groups also and then compare, because when you have double bonds, those double bonds can be between carbon-carbon or carbon-oxygen, and so you have to open all of those up from sp2 to sp3. So when you do that, your priorities might change. Okay, so please review these, okay, for yourself. I don't want to go over this again because we've done it. So here is a solved example, okay, for this, and I don't know again how much to go over this, except that again, just make sure that you slice the double bond into two, and then look at each atom. Okay, and then see which one is heavier. So in this case, the left side, chlorine is heavier than, not heavier, higher atomic number than carbon, and then on the right hand side, bromine is a higher atomic number than chlorine. So both are on the same side, and that would be a Z then, okay, or a Z, whatever. Anyhow, so do all of these, and then let me know if you have any issues with any of this. Just a few more things here before I move on is, first of all, look at this, how we name this is that the alphabet, whatever it is, E or Z, whatever, it's going to be in brackets. You also have to use the dash after the bracket. Okay, there's a comma between 1 and 2 if there is two things. So here there was 2 chlorine, so make sure you put your commas, dashes, and in the right places. All right, so the next aspect of alkenes is the stability of alkenes, and the way I look at alkenes is the more substituted it is, the more stable it will be. Okay, and what does it mean by substituted? It means that if you have R groups meaning if you have alkyl groups around, okay, the double bond. So the more alkyl groups you have around, the more stable it will be. We start getting into issues when you have only two R groups, because if you look at these three over here, um, these three, they have the same kind of R groups, but this one is more stable because both of the R groups are on the same side. Okay, so this could be seeming like a terminal alkene, okay, if you will. And then here, this is kind of considered to be, a trans and a cis. So I generally will not kind of push you towards deciding between these three, because it's kind of hard to remember whether cis is more stable or trans is more stable. But just know that, if you have all R groups around, that's going to be more stable than when there is none around, or one around, or two around. Okay, that's kind of what I need you to know. One last thing I want to mention about E and Z nomenclature also is that, when you have terminal groups like this, okay, then you cannot assign E and Z. Okay, because these two are the same. All right, so these ones are neither cis nor trans because they're the same groups. I know I was kind of a little bit out of context. Okay, and then degree of unsaturation. Now this is something that we talk about only when we have unsaturation, which is in double bonds and triple bonds. So a degree of unsaturation, 1 degree stands for 2 hydrogens. Okay. Alkenes are the most saturated of all hydrocarbons because they have all single bonds. They have the maximum number of hydrogens of any hydrocarbon. So anything less than an alkane would be considered to be unsaturated. Okay, and so generally a degree of unsaturation is 2 less hydrogens. And you will see that in a lot of the compounds that we deal with, it's always going to be an even number of hydrogens that's missing. Okay, so you go from an alkane to an alkene, you lose 2 hydrogens. You go from an alkane to a cycloalkane, you lose 2 hydrogens. Okay, so it's more of an even number kind of a thing. All right, so the degree of unsaturation increases as you go from an alkane to an alkene to an alkyne, because you're losing 2 hydrogens, okay, at the same time. So how do you actually figure out the degree of unsaturation for any random compound that I give you? So degree of unsaturation, which is also called hydrogen deficiency index, which I don't tend to use the word hydrogen deficiency index because I feel like the compound is maybe a little bit sick, so I prefer degree of unsaturation, but anyhow, it's up to you. You can use HDI if you want to. So what you do is you should take the total number of hydrogens that should be in an alkane for that molecular formula that you are given, subtract whatever is in that compound that you are given, divided by 2, and that gives you the degree of unsaturation. Okay, so for example, if you're given a compound like, C6H8, right, how many degrees of unsaturation there are. Okay, so we're going to do the calculation in the next slide. Okay, but this is kind of how you would do it. You will find out the number of hydrogens in the alkane. What alkane? Alkane with a 6 carbon. Okay, so if you have 6 carbons, then how many hydrogens should you have? You should have this number of hydrogens, 2n plus 2. Okay, so then once you have the total number of hydrogens, you should have an alkane, then the number of hydrogens you are given in that compound, which in this case is 8. Then you figure out, your degree of unsaturation, okay, from there. So what do the degree of unsaturation tells us? Okay, so if you have 2 hydrogens less, well, big deal. What does it tell you? So the 1 degree, okay, which really it literally is written like a 1 degree. 1 degree of unsaturation is either the presence of a double bond or a ring. Okay, and we've mentioned this before. I've said this to you before. So for example, C4H10, that is a butane, and then C4H8 would be an alkene, but C4H8 could also be a cyclobutane. All right, so which means both things are possible. So the degree of unsaturation doesn't tell you whether something is an alkene or an alkyne. it just tells you that you're missing hydrogens. Okay, that's all it is telling you. So, be aware of that. So how do you know that you have an alkene or an alkyne then? Well, in those cases, you have to do more tests. Okay, so this is something we do in what is called qualitative analysis. So in qualitative analysis, you have to do certain chemical tests which give you positive or negative depending on the color. Okay, so and then you figure out from there if you have a double bond or not. All right, so but otherwise degree of unsaturation just gives you an idea that you're missing hydrogens, but not if it is an alkene or not. So you have to figure that out eventually in the lab. Okay, what it's going to be. Either you use instrumentation for it or you use qual analysis, okay, for it. So something like that. So here, if you have a 2 degree of unsaturation, which means 2 degrees would mean C4H6. Okay, so C4H10 is going from C4. Let me write this over here so you don't get confused. So C4H6. So going from here to here is 1 degree. Going from here to here is also 1 degree, but going from C4. H10 to 6, that would be 2 degrees of unsaturation because you're missing 4 hydrogen, and 2 hydrogen is equal to 1 degree. All right, and that's why you divide it by 2 in the formula. So for 2 degrees of unsaturation, what is possible? Anything is possible. You can have a triple bond, you can have a double bond or a ring, you can have 2 rings, you can have 2 double bonds. So you have all sorts of structures possible, okay, when you have 2 degrees of unsaturation. Imagine what you can do with 3. So here is just a little bit before we do an example of unsaturation is what to do if you have some other elements in there. Okay, so for example, if you have a halogen in there, halogen can be interchanged easily with a hydrogen. Okay, so if you have 2 bromines in there, just go ahead and put 2 hydrogens in there. That's it. Okay, so the molecular formula for the first one here is C4H6Br2. Then you can just count that as C4H8 and go ahead and do your calculation. Okay, so C4H10, that is the alkane. Remember, I just showed you in the previous slide. So C4H10 minus this, that gives you 2 missing hydrogens divided by 2, and that's going to be 1 degree, okay, of unsaturation. If you have oxygen compounds, you can just eliminate that, no problem, because oxygen has 2 bonds or a double bond, and so it just kind of slides in there, and so you don't really need to worry about the oxygen. So whatever the molecular formula is for carbon hydrogen, you just keep that. Forget the oxygen, okay, in there. So as I've shown you here, you end up getting 2 degrees of unsaturation. You don't have to worry about counting how many bonds or how to replace oxygen. You don't have to. Just take it out, okay? Unlike halogen. For nitrogen is a little bit different also, because for nitrogen you have 3 bonds in nitrogen, so you have to subtract the nitrogen and also 1 hydrogen, okay, in there, because there are 2 connections. So here nitrogen, so if you have C5H9N for a molecular formula, then you remove 1 hydrogen and the nitrogen, so you will consider that as C5H8. Okay, and that indicates 2 degrees of unsaturation. So we will do the calculations. Here are some calculations for calculating the degree of unsaturation. So here is an acetate, and the molecular formula is C7H14O2. Calculate the HDI. Oh my God, I wrote HDI. All right, anyway, so degrees of unsaturation, whatever it is. So ignore the 2 oxygens because that's what we decided in the previous slide. So the new formula is just C7H14. So you find the alkane from there, which is going to be C7H16. So 14, you don't have to do the whole thing, just take the hydrogens in there. So 16 minus 14 divided by 2, and that is 1 degree of unsaturation. Okay, so pretty simple and straightforward. I have not had any of my students miss out on any of the HDI calculation at any time. Okay, and so I think you'll be fine. So just go through this one yourself. Let me know if you have any issues. Here, this is a little bit different kind of a problem, because now what we're asking you to do, we're asking you to draw structures also. So calculate the degree of unsaturation and propose all structures possible, okay, for this. So C6H10. C6H10 means that the alkane would be C6H14, which is then, if you subtract, that's 4 hydrogens that are missing, and that would be a 2 degrees then, okay, of unsaturation. So 2 degrees of unsaturation, as I gave before, these are the things that are possible, right? 2 double bonds, a triple bond, a ring and a double bond. So I've given all the structures here for you. These are all constitutional isomers. Okay, why? Because they have the same molecular formula. But look at all these different possibilities that we have. And so how do you know which compound you have for C6H10? Well, you either do reactions, which is the qual analysis, or you do some, use some instrument like IR or NMR to then figure out, what kind of compound you have. Okay. And now for the physical properties of alkenes. The nice thing about alkenes is pretty much they're same as alkanes. Okay, so nothing new over here. So low boiling points, and boiling point increases as the molecular weight increases. Again, they're low because there's all van der Waals forces. Alkenes are as nonpolar as alkanes were. So because of that, the solubility in water is pretty much nil, so it's not soluble in water. Because they're not soluble in water, we'll have to talk about density, which is then less than water. So which means it will float on water. If you had 2 layers, then alkenes will be the top layer, okay, in there. Now regarding the odor is just kind of a unique thing with alkene. Alkanes are a little bit more pleasant than alkenes. Alkenes can be good or bad depending on what alkene you're talking about. So here I've given you some examples, okay, for alkenes. So for example, camphor is a really nice smell. The smell of roses is also an alkene. So it's like, some are really good, and then some of them don't have any smell. Like linoleic acid, it doesn't have any, any smell. They're just fatty acids. That's all they are. Okay, vitamin A, which has so many double bonds, has no smell whatsoever. But aside the smell, let's look at all these things, because all these are alkenes, and these are all naturally occurring substances, which means that alkenes are quite prevalent in nature. Okay, so first let me just mention this group over here that I have. This is called an isoprene group. It's a very specific kind of a carbon skeleton. Okay, so you have these 5 carbons in there, and those 5 carbons, there are 2 double bonds in there. Taking this isoprene fragment, you get all these different compounds. These are actually classified as terpenes. Okay, terpenes, yes, if you can think of the word turpentine. Turpentine smells, right? If you haven't smelt it, it's okay. All right, but anyhow, terpenes is a class of compounds which is all based on the isoprene unit. The best example I can give you for an isoprene unit would be rubber, okay, which your tires are made up of, no matter whether it's a bike or trucks or car, whatever tires we're talking about, that tire is made of an isoprene unit. Okay, but many isoprene units, of course, not just one. All right, so it's a polymer of isoprene units. Isoprene units, when they combine in different ways, they can give us different smells. So camphor smell, of course, we know of. Pinene is a wonderful pine smell. So, these are beautifully wonderful smelling compounds. So terpenes generally will smell nice. Not all alkenes, as I said, smell nice. Okay, and by the way, tires, the smell that you get when somebody brakes really hard, and then you say that you can smell tires, or you can smell rubber. Well, that's actually not the smell of isoprene. That is the smell of sulfur. Okay, because sulfur is added to isoprene in order to make it stronger. Okay, so you can actually make tires out of it. That's called, anybody, you can think of the word? Vulcanization. Okay, so anyhow, all right, so let's not get sidetracked. So there are a lot of fatty acids also, as I mentioned before when I was talking about cis and trans, is that you have a lot of fatty acids that have double bonds. Now double bonds are considered to be good for your health, and the reason for them being good for you, double bonds, is because the double bonds can exist as cis and trans, and you can see how the structure is different when you have a cis versus when you have a trans. A trans will look like this. Okay, these are all cis bonds, and these are actually good these are good fatty acids for you. What happens is when you eat fatty acids that are all trans, they will be all like this, right? And then they have the carboxylic acid at the end. I'm just drawing a short one just to show you what's going on. And then when you eat, fatty acids, of course, even if you eat 1 mole of fatty acid, that's, 6.02, 10 to the power 23 molecules. So here's another one that stacks up, okay? And then another one that stacks up in the body, because the body likes to stack up all these molecules together to give them, less room in your body. When you're stacking them like this, okay, you can probably imagine what is happening to your arteries or your liver where everything gets digested. So you end up having what is this wonderful thing called plaque, okay, which is really not very good for you, and it causes heart attack and whatnot, okay, and so this is not good. But once you have something like cis, okay, double bonds, these cis double bonds, look at the way they are shaped over here. They will not stack up like this, okay, and so if they don't stack up like this means they're a little bit more free flowing. It means that they will not stack up, and they will, get out of your body a little bit easier than, when they are kind of close to each other, okay, because when they are packed together, it's a little bit harder to get rid of them also, okay. So that's the difference between cis and trans fatty acids. So always eat the trans ones, and cis ones, always eat the cis ones. And how do you know the cis fatty acids? The easiest way to know that you have cis fatty acids is liquid versus solids, okay, and so always eat the liquid fatty acids. So like olive oil is good for you, although vegetable oil is also considered to be a liquid, I mean, it is a liquid, but that's not very good. Generally, you have to look at the structure, of these compounds, and then see which one is more healthy for you, okay, because the more double bonds you have, the better it is. The more you have them in cis, the better it is, okay. So look for the structures before you eat fatty acids, okay. And then vitamin A over here also has a lot of double bonds. By the way, the double bonds are also important in your vision, and so here I've given you a link that you can go to, because your vision here is all dependent on the cis and trans, okay. That's it. So it's very, very, very important part of our life, and I think that's it for us. Everything that I've kind of mentioned here, except for the applications, which I think you'll remember, and even if you don't, it's okay, because that's not in the exam, but everything else is important for us.